In quantitative systems pharmacology, every model is a plumbing network. Drug goes into one compartment, flows to another, gets processed, gets eliminated. The math that governs all of it, ordinary differential equations, is just plumbing. Water in, water out, water level changes. Let's open the walls and watch the pipes. Welcome to the plumbing network. One tub, one faucet, one drain. The water level at any moment depends on how fast water comes in minus how fast it goes out. That's a rate equation df that equals inflow minus outflow. When inflow exceeds outflow, the level rises. When outflow catches up, the level holds steady, the rate meter reads 0. Every ODE-based model is just a bathtub with a faucet and a drain. Concentration of drug in plasma, the number of receptor molecules on a cell surface, the size of a tumor, they all follow this same logic. Input minus output equals rate of change. The drain flows faster when there's more water, that's mass action kinetics. The rate is proportional to concentration. Double the water, double the drain flow. The proportionality constant K is just the drain's efficiency. Now add a second pipe. If two chemicals need to meet and react, the rate depends on both concentrations. Rate equals K times A times B in QSP. This describes drug binding to a receptor. The binding rate depends on both drug concentration and free receptor concentration. More drug, faster binding. More receptors, faster binding. Most of the rate equations you'll see in a QSP model are mass action. Some drains have a grate. At low water levels, the grate handles the flow easily, it looks like mass action. But crank the water up, and the grate gets overwhelmed. It hits a maximum drainage rate, max, no matter how high the water goes. The water level where the drain runs at half its maximum. That's KM. This is Michaelis-Menten kinetics. In biology, enzymes process drugs this way. At low drug concentrations, elimination is proportional. At high concentrations, the enzymes are saturated, they can't go faster. This is why doubling a drug dose doesn't always double the effect. The drain is clogged. 3 tubs, 3 drains, 6 pipes connecting them all. The water flows simultaneously everywhere. No formula can solve this by hand. The system is coupled and non-linear, so the plumber pulls out a stopwatch. Check the levels now. Calculate the flows. Advance the clock by a tiny step. Update the levels. Repeat. This is numerical integration, Euler's method. But crude steps overshoot. The water level can go negative if the step is too large. Runge Kutta is smarter. It takes 4 quick sub-measurements per step and averages them. Almost every QSP model you encounter is solved this way. The computer is the plumber with a very fast stopwatch. 4 plumbing principles. Rate equations tell you how fast the level changes. Mass action says the drain flows proportional to the water level. Michaelis-Menten says some drains get clogged. And numerical integration is the plumber checking levels step by step because the system is too complex to solve by staring. Next, shortcuts for when the plumbing is too complicated.